Check. Hello, hello, check.
Okay, welcome everyone to today's seminar. We are very happy to have Biswajit Sahoo with us today. He's going to tell us about magnetized bounds for conformal field theories.
Thanks. Thanks, Ashok sir, for hosting me here. So today, as like advertised, I will speak about deriving some magnetized bounds on conformal field theories. And this seminar will be mostly based on this paper we recently put out with Christopher Harjog, William Pannell, and Andy Stargio. And this paper is based on kind of or inspired by various other developments in recent past. Like even some of them are very past. Like for example, even after the first paper of like Swinger, when he wrote down the propagator for a like free fermion in a strong magnetic field, people use this to compute various like effective field theories. And then also later, since in like in QCD or in setups where basically strong magnetic field is very important for quark gluon plasma and many other setups, people also try to extract some effective action by integrating out various degrees of freedom by putting some system in a strong magnetic field. So there are many examples along this direction. Then recently, there has been some development of considering conformal field theory with some global symmetry and then turning on some chemical potential, where basically usually the conformal field theory goes to some superfluid phase and people started constructing various effective field theory methods to study large charge expansions of to basically probe the large charge sectors of conformal field theories. Then also recently along the same directions, people tried to develop some dispersive arguments to bounce various effective field theory coefficients for some theories which breaks Lorentz invariance. And also very recently, some studies emerges like studying some conformal field theories, putting in a magnetic field and studying various properties of it. So all this kind of works kind of inspired to us to study the following questions, which I will try to answer in this seminar, maybe not fully, but partially. So the first question I would like to ask is that how does a conformal field theory respond to a strong background magnetic field? And then secondly, I'll ask that suppose we put now a CFT in a strong background magnetic field, now are the magnetic susceptibility and transport coefficients can take any arbitrary value or can they be bounded? And what are the principles or methods we can use to bound such kind of like susceptibility or transport coefficients? So basically, these are the questions I would like to ask and try to answer in this seminar. And to do that, roughly this will be kind of what I'm going to speak in this seminar. So I will take a 2 plus 1 dimensional unitary parity invariant conformal field theory, which will have some global U1 symmetry. Then I will put it, or I will gauge the global symmetry by introducing some background gauge field and also place the theory in some curved manifold. And in general, if we turn on a strong background magnetic field, usually we expect the spectrum will be gapped. So then we can integrate out this gapped spectrum and able to write down some effective field theory involving various non-dynamical background fields which are introduced, like the gauge fields and the background metric, which will allow me to compute various observables like current correlators, stress tensor current correlators, and various other things as a low energy expansion, because I could have an effective field theory which is valid below some mass scale generated by this strong magnetic field.
Sorry, question.
Yeah.
I mean, the gap may depend on whether the system has fermions and so forth, because in this, if you have these Landau levels, then there's a lot of degeneracy.
Right. So usually like for some free theories, like for free fermions, the ground state is gapless. But we usually expect that if there is some interacting CFT, the ground state like it will be elevated, like that the ground state energy should be non-vanishing. I'll try to give some arguments. Obviously, I don't have a very concrete argument.
Not the ground state energy. The gap is about the next one, right?
So okay, so
the next energy.
So the gap here, what I'm telling, I have a spectrum, and I'll just consider that, say, for example, the single particle states will have non-vanishing energy, or.
But I'm saying, you're saying typically, I understand there can be certain situations like this, but in these quantum Hall states that people study, they are like, I mean, maybe it's not a CFT, but some system with a strong magnetic field. Like there are, like this nu equals 5 half state or whatever that people discuss is supposed to be gapless.
Okay, yeah, maybe that's true. So all this philosophy which I will tell only works for the set of systems where it will become gapped. Okay, where if there are some gapless modes, then I have to also incorporate those modes in the low energy with the effective field theory, and also how they talk to each other I have to describe. So this will be a very complicated system. So my assumptions will be only this gapped spectrum assumption. Yeah, I will have some parameters. So yeah, the CFT could have. So this is basically, so there, if there are some parity, like if it is a parity odd thing, they could generate some chiral anomalies, for example. And also, as I will show, like one can write down effective field theory for those kind of things as well. But what happens is that those I won't able to bound using some dispersive arguments. So that's why I'm just restricting to parity invariant theories. Okay. And otherwise, yeah, one can write also.
Variance under charge reversal and time reversal.
So those I don't need. Okay, in 2+, yeah, I think only parity will be enough for me to construct the effective field theory. Those I won't make any assumptions about, I think, other symmetries, other discrete symmetries.
But the time reversal is broken anyway by the magnetic field.
That's true, yeah. Okay.
Yeah.
External magnetic field, yeah, that's true, yeah.
Charge conjugation, sure.
Maybe also broken.
V goes to minus.
Right.
Magnetic field. So then what do you mean by parity invariant? It's parity invariant without the. I thought it's parity invariant without the background.
So.
Which is why I was asking, without the background field, do you want C invariance and T invariance, or?
So for me, while constructing this effective field theory, I just won't allow any terms which are odd under parity transformation. So now this kind of makes me the assumption, or
itself you would want to be parity invariant.
Yes. So basically, if suppose I allow the CFT like is non-parity invariant, my feeling is that the effective field theory which I will construct, they may also show up this parity non-invariance. For example, if you consider like two-component Dirac fermion in 2+1 dimension, this is usually under parity transformation, it is parity odd. So that basically in the IR effective action, if you try to compute, it will generate some like anomaly term, which is like parity odd kind of terms. So I won't allow such kind of system. So then basically, once I have some effective field theory description which breaks Lorentz invariance, so now I'll try to develop some dispersive arguments, and I'll try to bound some effective field theory coefficients, and from there I'll try to argue possibly that how the magnetic susceptibility and other things are bounded in general. So let me try to give some arguments. None of them are very concrete. But why I expect that if I put a strong magnetic field in a CFT, the spectrum will be gapped. So first of all, turning on a magnetic field background can be think of as basically turning on a relevant operator, and the relevant operator is basically here the current operator of the E1 global symmetry, which is scaling dimension 2 in 3 dimension. And then I just introduced a coupling which is spectrum dependent coupling, this mu x, which is the gauge field. And then since I want to give a strong background magnetic field, basically what I want to do, I want to choose a gauge field configuration which basically gives the constant magnetic field. So this will be my deformation of the UV CFT. And as I was telling, if the spectrum will be gapped, then the IR theory will be empty. There won't be any degrees of freedom. But why do we expect that such kind of a spectrum will be gapped? So as I was telling, I don't have any rigorous argument, but I can give few examples and also some S-duality argument that why I will expect that at least when the matter and gauge couplings of the like some dual safety degrees of freedom are weak, then basically it usually goes to a Higgs phase, and that by that way I will be able to argue that for at least some set of systems, things will be gapped.
So are you putting the CFT on R2 or S2 or what is the spatial manifold?
So here to start with, I'm just considering the spatial manifold to be R2. Okay, but once I have the effect, like the say effective field theory in generic card background, I can put it to on S2 also and put some magnetic monopole and to give the background magnetic field and whatever I like.
Well,
So
I was not worried about the monopoles, but I was worried that if you're already on S2, there's already a gap set by R by the radius of the sphere.
Yeah, I agree. So I will only put on a background which are basically conformally flat.
Okay. So we can just imagine R2, right?
We can start with R2, but we can R2, and then there is another time direction. Spatial manifold is R2. Yeah. Okay. So first of all, like suppose there are some free CFTs like pre-complex scalar or pre-fermion. So there, if we put a magnetic field, we know the Landau level spectrum. Like for example, for the pre-complex scalar, it is already gapped. For the pre-fermions, however, the ground state is gapless. So some gapless degrees of freedom still remains in this case. But if we turn on some interaction, and for example, for this complex scalar, if we
I don't understand this statement. N equal to 0 is the ground state.
Right.
Why does the energy being 0 mean gapless? Gapless refers to E1 minus E0. Why do you say that E0 being 0 is gapless?
So yeah, the gap in a sense here I am considering that the IR, like the extreme IR, I should not have any degrees of freedom left. So if there is some, say for example, the ground state has like the ground state, if it contains some degrees of freedom, some degeneracies and all these things, right? So if the system has this ground state energy 0, still in the low energy, if I flow, some degrees of freedom left in my theory.
Well, the point, here you're not talking about degeneracy, you're comparing these two. You're basically saying on the left-hand side, E0 is non-zero, and on the right-hand side, E0 is 0.
Mm-hmm.
But that's not typically the statement of gaplessness. Gap refers to E1 minus E0.
Yeah.
And in both cases, it's non-zero.
I think the difference is whether you are thinking from the point of view of the first or the second quantized. Here I understand the gap means that no electron and one electron state has a gap. Because the ground state is no electron, right?
Mm-hmm.
Okay.
That has 0 energy, and then you have to put an electron, you add it to the first Landau level, and that will have a non-zero energy.
Yeah.
So you're thinking of this as a second quantized disk. Is that right?
Right. So in the ground state, I also can put energies, like put electrons, for example.
These have finite density.
Yes, they have finite densities.
Infinite number of.
They have finite densities, so the finite that depends on how many electrons you want to put, right?
Yeah.
Because if you have just put, imagine that in a vacuum, you put a magnetic field, right? Then the energy levels are getting quantized.
Sure. For
Single
electron.
And now you can put an electron here. It will have some energy, right? Which is the square root of 2b or square root of b.
Right.
So that in that sense there's a gap. That no electron and one electron will have a square root of b gap.
Right.
Whereas in the second example, the formulaic example,
Mm-hmm.
n equal to 0 is truly 0 energy, right? If you add a formula in that level.
Right.
You're saying the zero particle state in this formula, the zero particle state has been taken to have energy 0.
Yes.
And then you're trying to add one particle.
Add one particle on the
And
Landau
the
levels.
left-hand side will go to n equal to 0. So that is non-zero.
Mhm.
On the right-hand
Right.
side will go to energy.
That's
Yes.
That's the concept I can think of.
Yeah. This is what exactly. Yeah. So in that sense, this is basically like I can put electrons in the ground, like lowest Landau level, and it still remains gapless. And so
So these electrons wouldn't be like those fundamental electrons, but rather some Bosonic particles around this ground state or something.
Yeah.
Usually there will be a gap,
and
there will be a mass for the electron. But in this magnetic field background,
Mhm.
perhaps because you have infinite degeneracy, but you're not.
Mhm.
Bosonic particles will have a spectrum which starts from 0 and then continuously goes.
That is true. Yeah.
These are the first ones which you are talking about.
Probably, yeah. Because there's no mass term.
no, there is no mass term. Those are really like CFT. So
Because you are thinking of the mass scalar.
mass, yeah.
On which you have to match.
The electrons that you're talking about are really the quanta of this scalar.
Yeah, either the
Either scalar or for the fermions here also. And just to mention, like it is known that if you say like take like n copies of this complex scalar and add this interaction, then it usually flows to a Wilson-Fisher fixed point, and there basically a dynamically mass, like in presence of magnetic field, a dynamical mass generation happens. One can solve the gap equation and one can find it, and the mass is proportional to square root b, which here also adds a order 1 term, which is fine, like which is still remains gapped. But here the gapless, like the free theory was gapless, but if you also add a like this psi bar psi to the power square whole square term and goes to the IR fixed point, which is a Gross-Neveu model, and turn on a magnetic field, it also generates a like order 1 term for this psi field. Then the mass term is again proportional to square root over of b, and basically the ground state energy level is now non-zero. So the lowest Landau level is now have non-zero energy, so the system becomes gapped. So this is
again a bit unfamiliar.
So, okay.
Sorry to slow you down. So let's focus on the left-hand side.
Mhm.
So just saying you take NB scalars
Yes,
and you add this interaction term,
yes.
and you still turn on the strong magnetic field.
Yeah, I first want to flow to a like Wilson-Fisher fixed point, which is like the IR fixed point, because I want to have interacting IR CFT
Then you turn on the
magnetic field.
that. And then what are we saying? That you're saying that there is in that theory now?
In that theory now, I'm studying what are the Landau levels in large N expansion. So, and what happens is that, this, you define a bilinear field like psi bar psi to be the sigma field, and which generates the U-cover term. And basically, if you solve the mass gap equation, this sigma get a non-vanishing vacuum expression value, square root over of b, and that generates this mass basically. And then basically, if you now solve for this psi, like this phi system, the Landau levels, you will see that it is basically order 1 square root c, because basically it becomes generates a mass term.
But
Square root over b.
Wilson-Fisher CFT still has particles. So in the free theory, we have these particles.
Right.
But in the Wilson-Fisher, it's an interacting CFT, but I guess at infinite n, it's still free.
Mm-hmm.
So that is why you can talk of this single particle spectrum.
Uh,
That was the previous explanation that we did.
Right.
It's important that the theory is free.
Right.
So you can just talk about the Fock space.
Mm-hmm.
So in this case, something like that must also be happening for you to write a similar formula. You are assuming that, so the NB goes to infinity is really important. That means maybe in that.
Yeah. So in the NB so what happens is that now this theory will again be described by these phi I scalars, but it will have a mass, a mass term will be generated for that, like 3 really in large N limit.
Massive scale.
Exactly, pre-massive scalar, NB number of pre-massive scalar. And this mass is given by the square root over of b basically. So in that sense, yeah, just to demonstrate that when you turn on interaction and at least some interacting CFTs, usually in the large N limit, one computes and finds that, for example, at the free fermion case, it is now the lowest Landau level is gapped basically, or have finite energy.
Number that functions of lambda and mu?
Yeah, the lambda star, basically the coupling at the Wilson-Fisher fixed point, and also it also what is mu? Sorry, mu can actually mu at the Wilson-Fisher fixed point basically goes to 0. Like basically it's just, and basically it's function of this lambda star, which is the IR fixed point value, and also magnetic field. Okay, so this is one of just to show an example that how a free theory becomes gapped when you turn on an interaction and goes to an interacting fixed point.
So even though the magnetic field, there is a dynamic mass generation, right? So
even in
not at the fixed point.
Not at the fixed point, right? Fixed point, it has to be massless because it's a IRCFT fixed point. So there should not be any mass parameter. Okay, so these are just some examples. Now let me try to give a more, not still rigorous, but argument that why I would expect that the CFT will become gapped. So for that, I will use this S-duality argument, first discovered by Peskin and then also Dasgupta and Halperin. They also extended it. So let's consider again like a 2 plus 1 dimensional CFT with a global U1 symmetry, which also has a conserved current J mu, and then gauge the current by introducing a background gauge field mu and define the partition function by integrating out the CFT degrees of freedom. And the argument says that there is a dual, there will be also a there will be a S dual theory for for this CFT, which will be a gauged which will involve a gauged matter. There will involve a gauge field, which I am denoting by mu, and this gauge field is dynamical. So the dual theory action, let me write in this following form, phi, which is a functional of phi tilde and mu, and it has a dynamical gauge field, and there will be a topological current which basically acts on this monopole operators, blah blah. But this current has this following form, and then the S duality tells us the partition function of the original theory can be written as the partition functions of the the dual theory, but you have to add, basically you have to introduce you have to basically gauge the topological current you have for the S dual theory in the following way. So this is the statement of the S duality. Now what I want to do, I want to study this system by turning on a constant background magnetic field for this curly A field, which basically tells that I will choose this following background, which basically turns on the constant background magnetic field. And then I want to see what its behavior, or what it tells about the original CFT partition function. Okay, and in general, the argument they give is basically when you turn on a magnetic field configuration for this gauge field, it basically turns on a chemical potential, which basically the A0 component non-vanishing here, and then at least when the gauge and matter sectors are weakly coupled, then basically you can think of this matter sector goes to a superfluid phase, and then finally this superfluid degrees of freedom will be eaten up by this gauge field, and basically the whole system goes to basically a Higgs phase. So this is kind of a general argument. I will give an example how it exactly works. And this basically tells that since in the dual theory it goes to a Higgs phase, that basically tells the original CFT basically can be argued to be gapped. But in all these arguments, it is very important that we had to assume that the matter and the gauge sector of the dual CFT is basically weakly coupled. So just to give an example, this is take this complex scalar model again, basically which is known as this XY model fixed point of this Wilson-Fisher CFT, and take this theory and gauge it introducing this non-dynamical gauge field again, and the S-dual theory is given by a gauged complex scalar model with the following action. And then I want to substitute this action here, and then I want to argue that how the original CFT will be gapped, whether one can argue by turning on this gauge field which will give a constant background magnetic field. So what happens that if you turn on this gauge field configuration to be this blackboard A, which gives the constant background magnetic field, this term which was this BA kind of coupling basically becomes V over 2 pi A naught, and then basically in the path integral, when you integrate out this age, like the A0, which is the time component of this dynamical gauge field, if you integrate out, that basically restricts to a field configuration of your path integral given by this following equation. And if you consider this phi tilde, which are the matter sector of this dual CFT, to be time independent, then basically it tells that this A0 value, which is the zeroth component of this dynamical gauge field, takes a non-vanishing value proportional to B, which basically tells that it basically introduces a chemical potential to your system. And once you have a chemical potential to your system, basically now the gauge symmetry, the U1 gauge symmetry of this gauge theory basically spontaneously breaks down, and basically it goes to Higgs phase. In a sense, if you just expand about the vacuum for this phi tilde field, and this e to the power theta of x, which is basically the Goldstone boson of this matter sector global U1 symmetry breaking, that will be eaten up by this gauge field, and the gauge field becomes gapped, as well as this rho, which is the fluctuation about the vacuum, also become gapped. So basically the full system basically goes to a gapped phase, which basically in a sense through S duality basically tells that the starting the original CFT also becomes gapped in a constant background magnetic field. So these are kind of, but again, while arguing this thing, I had to assume that this gauge matter coupling G is basically small, so that I can able to systematically argue that the superfluid, the Goldstone boson will be eaten up by the gauge field, and to bring it to the Higgs phase. So yeah.
This is is it fair to say that this is special to 3D? This A0 times B argument, because
No, it's not special to 3D. I think it's even in 4D also. If you turn on a like A0, the A0 component of the gauge field, it basically generates a negative mass square term. So basically, from that you can able to show that the U1 gauge symmetry is broken and goes to Higgs phase.
no, I was asking from the perspective, you're coupling the current JU, which is some epsilon del A,
Right.
to A.
Yes, yes.
And you want to pick up a magnetic field from that. That's why you want to turn on a magnetic field.
Yes.
Which on A0, just the A0 component only in 3D, right?
That's true for the B atom, yeah. Even I don't know whether this S duality argument also only is this argument only true in possibly in 3D also. I don't know whether this is only in 3D, right?
Will be only in 3D, right?
Mm-hmm. This kind of B atoms only can be written in 3D, yeah. Yeah, so maybe from that point, okay, maybe it's 3D. But this, if you have like people independently studied, for example, 4D CFTs global symmetry and turn on a chemical potential, there you can show that it again goes to superfluid phase. Like suppose that if there are no gauge fields, if there are gauge fields, then it becomes Higgs.
So roughly can I think of this as a Janssen stem because it is literally a wedge.
Yeah, it's kind of a Chern-Simons stem, but there are two different gauge fields, right? One is a background gauge field, and this is also a dynamical gauge field. So it's interaction. It's kind of a kind of interaction literature people usually tell. Yeah. Okay, so why do I? So because I want this lambda 5 term. Sorry, this is 4. This should be 4. Okay, not square. Sorry. So I want this lambda 5 for interaction to have a potential which is like Mexican had to have this goes to the superfluid phase. So that's the reason basically I gave this example. Okay. So, okay, these are kind of some rough arguments why I would expect that for a interacting CFT by turning on a magnetic field, it goes to a gapped phase. But but there could be some systems which I don't know could remain gapless, as Raghu was pointing out maybe. And for those kind of systems, whatever I'm going to tell now won't work. One have to be more careful and incorporate these massless degrees of freedom also in the low energy theory. But for a moment, yeah.
Just in the free example, could you say why the mass scale was square root of V? Because the cyclotron frequency is linear in V.
Yes.
And here, because
so
the particles are relativistic, and so there is some square root.
So what happens is that the magnetic field is basically mass squared dimension. And so basically,
it's important that you're doing relativistic particles.
Yes, maybe, yeah.
Right? Because otherwise, the
massless particles.
These are massless particles, and as well as And since there is no other mass dimension in my theory, so since B is mass squared dimension, so only possibility square would be is the energy. Okay. So now I'll try to describe. Okay, so now I'll assume that my spectrum become gapped, and I started from a conformal field theory, which is a global U1 symmetry. And then I want to construct what is the effective field theory involving these background fields. So this is basically again the same picture. I want to start with a 2 plus 1D CFT with a global symmetry, and the parity invariance basically will tell me that whatever effective field theory I will construct that should contain even number of derivatives. And also it will tell me that there won't be any anomaly terms like while anomaly are not present in odd dimensions. Also chiral anomalies are like in 3 dimensions are always odd number of derivative contains. So I don't have to think about those kind of situation. And then what I want to do is basically I want to gauge the global symmetry and conformally couple the theory to a non-dynamical background metric and define my connected functional by integrating out these like degrees of freedom after placing this theory in this background. And if you want to go back to the CFT like currents and the stress tensor, you can just use the following variations. Now, let us remind that since our theory we placed like conformally coupled to the curved background, so it is while invariant, deep invariance, and also the gauge invariance is intact because we just gauge the global symmetry. So whatever the connected functional we will construct, they should have this following like invariances. So now, in general, since if we don't turn on any constant background magnetic field, we just gauged by introducing some gauge field. So this connected function in general is non-local. However, if we turn on the following gauge field configuration, there is a gauge field given by this A mu, and there is a fluctuation which is the another A mu. So this is curly A, this I will call blackboard A, and this is the usual A mu. So that this blackboard A piece, which basically corresponds to this constant background magnetic field, given by the magnetic field is given by B, and then under this assumption of this gapped spectrum, then whatever this W I will construct, if I expand in this mu, this should generate a local effective action because the spectrum is gapped. And the effective field theory will be valid up to the energy scale given by the mass spectrum or the gap of the theory, which will be usually proportional to square root over B because there are no other scales in my theory.
This mu is a background field, classical background.
So this is a classical background field. This one, yeah, this one is also non-dynamical, some fluctuation over this constant background magnetic field. So this won't play any role. It will just help me to take variation of the effective action and to compute various current correlators. That's the whole purpose of it. Okay. So
ensuring that all elements are zero and choosing appropriate field.
Exactly. So just staying in the parity sector and working in 2+1 dimension. There won't be any other anomalies.
To ensure parity anomalies are zero,
Mm-hmm.
you have to gauge a huge global symmetry. You have like Emmy or
Mm-hmm.
So you are assuming that all those things are still allowed in normals. It's just that the U1 gauge field is non-dynamical, and that's what you have taken as theory.
Yes, yes.
This CFT
CFT can have also, can have any dynamical gauge fields, but since those will be gapped, like if they are present, if I assume that they will be gapped, so those degrees of freedom I will again integrate them out. So that's why only in terms of these background fields, if I try to write, there won't be any global U1 anomaly. Yeah, this is the only.
The CFT itself has say a U1, say electromagnetism sitting inside it.
Right.
So integrating that out as well.
Yes, yes. Because I'm assuming that all the spectrum, all the degrees of freedom will be gapped along the RG flow.
I thought this U1 is that global.
So there is already one U1 which is global. I'm not gauging it. So the CFT has a global symmetry. Now suppose this CFT may have some other extended symmetry and some like global symmetry that is gauged. So for example, with some dynamical gauge field. So those could be there in my CFT. But the only assumption what I'm considering is that once I turn on magnetic field, I will consider that the full spectrum like becomes gapped. So no degrees of freedom left. Then I don't expect any anomaly to appear for my effective field theory constructed out of this.
If the theory, let's not talk about U1 since there is already a U1. If the theory, for example, had an SU2, you would assume that it is Higgs already.
Yes.
Well, the point is, if you have SU2 gauge fields, the SU2 symmetry is not a symmetry that acts on the Hilbert space. The operators are
singlets of that, yeah.
In this sense, that will not count as a global symmetry.
Sure. Yeah.
But if you have a Dirac fermion, it has usually a parity.
No, but single Dirac fermion it has. But if you consider two copies of like Dirac fermions with both parity or sector, which is the 4-component Dirac fermion in 2+1D, then actually there is no like anomaly. Parity assumption, yeah.
Right. So you have to choose field content appropriately.
Yeah. So that's my starting point. I will only consider parity invariant CFT. So I'll choose the field content so that in the CFT level there won't be any. Yeah.
So you could consider a CFT with gauge fields of some group, but then you want an ungauged global.
I want an ungauged global U1, yeah.
One is from this point of view, you can't even tell if the theory has a gauge field because
Yes.
why is this abstractly defined CFT?
Yes. Yeah.
But in what description if you have a gauge field?
It may not be, yeah. Right. So basically, then I have to use these following like properties that the connected functionals should be while invariant, they should be gauge invariant, and also this I could have just introduced my integrate out the degrees of freedom in flat background. So whatever the connected functional will be, I would expect that if I put in a flat space-time background, that should be finite. So there should not be any divergence if I expand about flat background of the metric fluctuation. And using those properties, one can able to see what are the possible building blocks one can use to construct such kind of a diffeomorphism invariance, gauge invariance, and while invariant effective action. And it turns out that the kind of things you have to use is basically the field strength tensor, which is invariant, gauge invariant, and don't transform under while transformation. Then you can construct a while invariant metric, which I am denoting by this g hat mu nu, which is basically f times g mu nu, where this f is constructed, which is basically the f squared term, and it transforms under while transformation goes like e to the power minus 2 sigma, and g goes to e to the power plus 2 sigma. So that's why g hat is basically while invariant metric. And since we have those two things, now at the curvature level in 3 dimensions, as you know, Riemann tensor basically are determined by the Ricci scalar and the Ricci tensor. So the only independent terms are like curvature is basically the Ricci tensor. And then there is also
So this R hat mu nu is the Ricci tensor
for G hat metric. So this is
G hat is the square root G.
no G hat mu nu is basically f times G mu nu.
Yeah, but since you said it's while invariant, it's square root G and G. No, there are G.
Sorry. So as I was telling, here this f is a square root over of this object, which is a diffeomorphism invariant scalar, but it transforms under while transformation because this inverse G transforms, right? It goes to like G lower goes to e to the power 2 sigma, so inverse goes to e to the power minus 2 sigma. That's why this f transforms like e to the power minus 2 sigma times f.
Why is curly f mu nu tensor?
That's the definition.
Which one? This curly f mu nu? So because I want to construct a effective action involving the gauge fields, so here not even the effective action, I am constructing a connected functional. So this curly f mu nu, right, it's a object which is invariant under while transformation. It's also gauge invariant object.
Why does the while invariance of the metric have to talk to f mu nu? Okay, maybe it's a basic term.
Because I have to write a action which involves both gauge field and gravity field. So they may talk to each other, right? In card background, if I want to write something which is diffeomorphism invariant scalar, they talks to each other.
I think what Godwin is asking is instead of this f, you could have put determinant of g to the appropriate power.
Exactly. Yeah.
That would
That's
actually
not transform covariant. Oh,
Yeah.
not transform the
Okay.
Right. Yeah.
You have while invariant but not general coordinate.
General coordinate invariant, yeah.
Whereas this is really tensor.
Yeah, because I can operate, say, nabla hat muse on this and to contract various OS. Those terms are also allowed.
And this is the only way you can do while invariant and covariant.
So those are the symmetries available to me. Then I can there is a more generic way to do it. It's called CCZW construction, which basically how some space-time symmetry and global symmetry basically breaks, and you can use it. But one can show that both constructions are equivalent. So this is the simplest way to do it, basically.
Based on this material, write the general effective action.
Yes.
F mu nu g hat.
Yes. So once I have those terms, then only I am left with just diffeomorphism invariant. So I have to just use these objects to build a diffeomorphism invariant action. That's all. I will order or derivative expansion. I will try to write all the terms. Okay. So yeah, it turns out that at least working in Mathematica, yes, sir.
Typically, when you do a wire transformation, the scalar fields, let's say that are part of your system, transform with some way.
Right.
The sigma times is that.
That's true.
This A does not transform under the wire transformation.
No, the gauge field don't transform the wire transformation because
That's easy to see. I'm sure it's correct.
Yeah, I think it's so I think it's like this. So you can how you introduce A, right? So you introduce A by, let's write it down, G mu nu A mu times the current, right? This is how you introduce J for the theory. Now in a CFT, right, the current, sorry, yeah, mu nu, sorry, thank you. So now in a CFT, right, this object, like under while transformation, goes like, so you may think that this is a dimension d minus 1, so roughly it looks like minus 2 sigma j nu. So there is a square root over minus j, I should also include here. So this is how it looks like, that this is how it transforms, but since this is a spinning object, so right, so this basically transforms actually minus 3 sigma. Okay, let me count if the argument is correct. So then this under while transformation goes like d cube x. This object gives me to the power 3 sigma square root over minus g. Okay, I think the argument I am giving, sorry, this is, I think the j mu upper is basically how this stands, sorry. Okay.
Is this just saying we have to just
So this is how j mu transforms, and then this 3 sigma, so this combination have to be 3 minus 3 sigma, and since g upper mu transforms like this, so gauge field won't transform under while. So this is the way one can
J mu transforms in a specific way.
specific way.
And it's important to keep the spin of J.
Exactly. Just not the scaling dimension. In 3D, yeah. Yeah, this is in 3D. In higher dimension, obviously mu will transform in it, but okay, no, maybe not even. Even in any dimension, I think this will transform like e to the power minus d sigma, and this will be e to the power d sigma cancels out. Even any d mu won't transform under while transformation.
There's another point of view in which any matter field is widely invariant. Because if you look at the stress tensor, for a scalar field, has two derivatives. So it will transform the opposite weight as g mu because delta is by delta g mu.
Yes.
So that will be covered by just the derivatives, through an overall scaling of the coordinates. So the scalar field will not contribute to that. For instance, even scalar field, even if it has a dimension, the while transformations, a natural way to give that is
For stress test.
by looking at stress tensor argument. Scalar field itself will not transform the while.
But you have a root G also, right?
No, I think scalars will transform under gauge transformation. That's why T mu nu has to transform in a certain way so that the 1 over square root over minus g definition like will be taken care of there. Otherwise, for example, if you want to couple free scalar to a curved background which is while invariant, you don't need to add this r phi square term if phi don't transform, because phi transform, that's why you had to compensate by this r phi square terms to cancel the interest rate.
I think it's true that in 2 dimensions, the stress tensor does not transform under Y.
Okay.
Just no while anomaly in bracket quantum. What is the link?
Oh, so in even dimensions, usually when you compute this connected functional, it's not while invariant. So because of some like you can argue different way, like some path integral measure you cannot define in while invariant way, or there are some kind of terms in the connected functional which appears to be non-local, which are not while invariant, and you won't have a local counter terms to get rid of. So there are many ways to argue, but in even dimensions, they usually are not while invariant, and usually you.
From this perspective, can't you adjust that rescaling as rescaling of Emmy? Like let Emmy also transform into that one and make this term.
But I don't want mu to be transformed. This is how I introduced. So you see, how I introduced my gauge field in the CFT is by adding this term. So in this, I want now after, and then I want to put the theory in a curved background. That's why I introduce this square root of g. Now I want my starting point to be while invariant after the gauging thing. So basically, then it tells that I cannot transform mu. Mu under while transformation should goes to mu. So I cannot change this. So anomaly, like just introducing such kind of a like action, local action, like add something and you cannot get rid of it. It's some intrinsic property, like so. Yeah.
Is when there is a while anomaly, the transformation of JU will also be anomalous.
That is true, but I'm saying in this case, the transformation of JU,
yes,
you determine before you even couple it.
I agree. And then you determine the transformation of mu as
from this, yeah.
And in the case that, I mean, while anomaly is not a physical anomaly, right?
No, it in curved background it's a physical.
Not like a gauge anomaly.
No, it's a sensible theory because those are non-dynamical curved background I introduce. I'm not putting the theory in a dynamical curved background. If I put it in a dynamical curved background, then it's a problem. Like, for example, this global anomaly is there, but if I want to make the mu gauge field to be dynamical, then there will be a problem. I cannot gauge it. Like, for example, yeah.
I think the statement of no while anomaly is just that this W of A that will be constructed will be while invariant.
Exactly. That's what it means.
The statement of the while anomaly would have been that W of transformed G will not be the same as W of G.
Exactly. And that appears only in even dimensions.
Yeah. What I was saying is that can you not make a new while invariant statement even when there's a while anomaly?
No.
I don't think no.
Compensating that with transformation of AB.
No.
then there will be no action.
Yeah.
It's really some physical like property. You cannot get it.
Anomalies are defined up to local computer.
Mhm.
The anomaly is what's left after you've taken out everything that you can by local computer.
Yes.
And whatever is left then is really, in some cohomological sense, like really physical. Cannot be removed.
Yeah, I mean, they knows about coincident points of the CFT. When you take two operators, say three operator correlation function and take coincident point limits, there are some particular contact terms. They know some OP coefficient. They are determined by some OP coefficient and some CFT data. So those are really some physical quantity. You cannot get rid of them. Anyway, so okay, so yeah, it just turns out that it is useful instead of working with this tensor, define a vector by which is basically the dual vector of the field strength, and that this f hat mu is also while invariant. This if you define this way, and this epsilon is basically the like 0 1 like 0 1 2 is basically plus 1 when you take mu to be 0, nu to be 1, and rho to be 2. This is plus 1 with this, and this is the particular square root of g you need to include to make it a tensor. So then basically it turns out make it a vector which transforms nicely under general coordinate transformation. So then basically you have all these basically building blocks. Now the goal will be to write down like in a derivative expansion the effective action. But also we don't want to include the terms which are related by integration by parts, and also we want to use this Jacobi identity to get rid of some of the terms and also some properties of this f hat which are there. So then if you try to play this role, it turns out that you can write at zero derivative level. So these derivatives are basically the derivatives of the metric and the field strength vector. Those are the derivatives which I'm counting. But inside the field strength, there are also in terms of gauge field, there are derivatives, but those derivatives I'm not counting here. And so it can be written as like the first zero order derivative level, there is a single like the single term with a single Wilson coefficient C0. And at 2 power of derivative level, there are 3 such kind of independent terms you can write. And at 4 derivative order, you can write such kind of a 28 terms using all these arguments which I earlier described. And just to give few examples, like the zero derivative order is basically the simple thing. You just write a cosmological constant term with the G hat metric. At 2 derivatives order, like write the Ricci scalar, some coupling of the Ricci tensor to the field strength vectors, like the dual vectors, and there is another term where basically some covariant derivative operating on the field strengths. And then at 4 derivative orders, you can also write such kind of terms. There are 28 such terms.
If you are not counting, why are you not counting f hat as having a derivative?
There is, right? So this is f hat has a derivative.
I'm saying that f hat was actually a derivative of the gauge.
Right.
But you're not counting that.
Oh, because this f hat, I will consider this expansion about a constant f, right, which is constant magnitude, and then the fluctuation. So since you start with a constant thing, that's why I'm not counting. Oh, this is just a choice. Like so. So basically, this paper tried to construct up to 2 derivative order these terms up to some errors, but then just to match with them, we just take this particular combination. There is nothing, no other reason. Because I am parity invariance, yeah. So only even derivative terms I'm just writing down. One can write down actually what derivative terms.
This number, this number 28, you know by the construction, or is it?
Yeah, so it's really playing with these identities and first writing down all the possible terms, then basically use in Mathematica basically how they are related by integration by parts, and using this various identity, we could basically, yeah, one can actually, there are some procedure like Siraj and these people, like for example, constructed this thing. We should have done this, but it's just kind of playing with Mathematica and using all these constants we settled to 28. So, okay, so finally now once we have this connected functional, basically to get the effective action, basically we have to, as I was telling, expand this curly mu in terms of this background mu plus a fluctuation. Okay, so now once we have like this effective field theory construction, which is valid up to the energy scale square root over of b, we can ask what are the observables so we can compute from this effective field theory and what we can do with it. For example, one of the interesting observable one can compute is basically the sphere partition function. So basically, you start with R3 and do do the following transformation, and it basically goes to up to while factor R3 goes to R cross S2, and in the R3 if you put a magnetic monopole at the background with the field configuration given here, so basically then this in this R cross S3 picture, basically the scaling dimensions of this, okay, so obviously the monopole operator here is like completely background monopole operator, but okay, I should not go to this monopole scaling dimension. But what happens is that so there are like basically this scale, the dilatation operator goes to basically a time translation operator, and basically then in this background we can evaluate the free energy by compactifying the time direction with a like tau plus beta and define this free energy, which is basically the free energy of the CFT at strong magnetic field putting on a sphere. And basically then it turns out, so, and this Q basically represents this magnetic charge for this magnetic monopole. And then basically it has a expansion of this free energy, which starts with Q to the power 3/2, which the coefficient is basically the leading Wilson. Q is the magnetic charge of the monopole. In general, it's quantized.
Right. S2 times R.
S2 times R.
S2 has a radius.
S2, yeah, S2 has a radius L, I think. L is the S2 radius.
What is L?
So this is just a coordinate term. So there was R3, and then I just did a coordinate transformation. I introduced this scale L, which is basically the size of the two sphere.
L is arbitrary. Basically.
L is arbitrary,
The only thing
basically.
that's meaningful is combination.
Combination of this object, which is this magnetic charge, basically. Okay, so now
But there is also an energy scale which is just 1 over L. Right?
The beta, the combination of beta and L will be
Also there.
also there.
Beta over L.
beta over L, yeah.
But okay,
It's like beta squared over B and beta over L, 2 dimensions.
Yeah, there are 3 numbers.
beta and
E.
B, right?
Then you can make 2-dimensionless combinations.
Right, but what we do is that we choose this background and evaluated this effective action on this background, and we saw that like only the Q is the only parameter appears. The total like energy density, if I multiply by L, only it is expanded in the Q.
That can't be correct. Let's say you set Q to 0.
Yes.
Then there should still be some, typically there is some Casimir energy left over on our spheres.
That's true. That's
So
true.
that should be captured by L E of B being some number. That is a pure CFT number without the magnetic field. People think about this kind of.
And what happens to these divergences there? It's a Q to the minus R.
So this is a large Q expansion. You cannot use this to put at Q equal to 0. It's a large Q expansion because this effective field theory is valid.
Then somewhere.
Yeah.
RQ is low derivative.
Sorry?
That's why the Wilson coefficient appears like this. RQ means derivative expansion.
Exactly. So it's like a momentum over square root over of B is the expansion, or the derivative over square root over of B is the expansion parameter basically. So so what happens is that suppose take part of the effective action, say this square. So okay, there is this C0 S0. Okay, so if you just substitute this square root over of G hat, it just becomes okay. Maybe I should show the G. So okay, here. So for example, if I turn on a constant background magnetic field, then this F is basically proportional to B. You're right? So this G mu nu is basically proportional to B, right? And then this S0, it's 3 dimensional, it just becomes B to the power 3/2, right? Then this term is basically involves 2 derivative because Ricci scalar is there, right? So in the background, it basically gives now basically this like the terms which gives the length scale L, right? Which is 2 derivatives will give 1 over L square, right? And then basically this tells that basically now you have to reduce 1 power of magnetic field to have the same dimensions because these Wilson coefficients are dimensionless objects. So this is basically how this expansion goes. Basically, it's a expansion in power of Q, in large Q expansion. So there is.
Using this, you cannot extract the Q goes to 0 level.
No, I cannot extract. I already consider Q to be the largest scale in my theory, like in constructing the effective field theory.
And these C0s and etc. determine how?
Those are really some theory dependent parameters, right? So those are Wilson coefficient. I don't have any, like, different CFTs will give different numbers.
Can you compute it for some?
Yes, for some theories I also at the end I can compute them. Okay, so now once you have the free energy, you can compute magnetization, and from there you can compute the magnetic susceptibility. For example, the magnetic susceptibility is given by, since it's a dimensional number, so it's square root over of B times the variation of this free energy with two variations with respect to the magnetic field B. But this usually when you define susceptibility, we consider really variation of this B and put B equal to 0, right? This is how we define. But this susceptibility, what I'm telling is the susceptibility at strong magnetic field limit. So that's why this, after evaluating this, I will take really large Q, or B going to infinity limit. So in general, this leading power, basically then the magnetic susceptibility is determined by the C0 coefficient. So if I can able to show that C0 is positive, negative, or what value it takes, this basically tells me that if I have a CFT and turn on a strong magnetic field, whether it goes to a paramagnetic, diamagnetic, or ferromagnetic phase. Good. So another observables which we can compute, like, are basically some sets of correlators involving stress tensors and currents, because we have this background metric and gauge field taking variations. But as I was telling, the effective field theory is basically a derivative expanded effective field theory. So if you take variations, only the contact terms will be there of the kind this from this correlation function. Or in momentum space, this really tells that it's a polynomial in momentum expansion. And also, since we use the symmetry, like Weyl symmetry, diff, and gauge symmetry, so basically those should show up as your word identities, and one can check where they satisfy, like there are very much interrelation between them, and they satisfy word identities. So one can able to then use this word identity to construct the possible independent tensor structures they will have in momentum expansion with some spectral density independent things. For example, yeah.
So this is the value at the background, right?
Yes.
But if you compute the one loop determinants and so on, they will have some contribution at large Q.
So exactly. So some So what happens is that if you even say, take this pre-boson example, which is we know the spectrum is gapped, and you can compute putting on a sphere explicitly, like integrate out these fields, and you'll have a determinant of this operator, like this kinetic operator with this background gauge field. And you can compute this, evaluate using eigenfunctions and all these things, and you will have a answer which is valid for all ordinary magnetic fields. It's a compact answer. Then you can expand this answer in magnetic field, and you will see that it starts with q to the power 3 by 2, and it expands in power of q, and there is no log q or q to the power 0 term. When the ground state Landau level is non-gapped. Yeah. If there is, like, for example, if you start with a 2-component Dirac fermions or like 4-component Dirac fermions, there is the lowest Landau level is gapless. So there you will get a log q.
Even though you have a mass scale, but there's no gap there.
Because there is a ground state or yeah, there is a.
If you don't put any deformation, right?
Deformation, not even magnetic.
No, put the magnetic field.
Oh, but not other.
No other deformation.
Yeah, like that is part of 2NP, right? So n equal to 0, I have very easy variance.
Yeah.
Even for a strong line.
Strong magnetic.
Yeah,
that have logarithms actually, if you compute.
So loop correction from the fluctuations over that background will just change these things.
No, it's already included.
It's already included. This is the full partition function. On including all the things. Yeah. So like.
So it's not just the previous formula which you gave for the effective action evaluated on the map.
Exactly. This answer is just that.
No, it's that plus log corrections. I mean, sorry,
if there is.
So C0 will have.
But the loops are already included because when I'm constructing the effect. Yeah.
For the background.
Background magnetic field.
And the CFT fluctuations are all
already integrated out.
The confusing aspect that you said you'll expand around the background, and what about the expanded part? The small Emmy part.
So here I am setting the mu is to be like the only I have the bold mu, but the fluctuation is 0 because I'm just evaluating. Sorry, I should have. Yeah, here you see there is no this f mu nu. So only I have the background thing. Exactly, and that is. So no, so I won't study dynamics of the fluctuation. So the main purpose of introducing this fluctuation is that I will have the effective action in terms of fluctuation, then I can take variation of this to compute various correlators. Yeah, that is the only purpose. Yeah. To find the correlation function.
Current correlator of the CFT itself.
Yes.
In
No,
the deform.
in the deformed theory.
Of the CFT, the CFT currents.
Yeah.
We are not changing the theory, we just put the background there.
For these C's, you will have to calculate root diagrams.
Exactly. I'll show actually in 2 examples that, yeah, to find this is. If you have the microscopic description of the CFT, you can compute it. If you don't have, obviously, yeah. I can put some bounds at least, what else? Yeah. Like this Wilson-Fisher fixed point of this Gaussian model, one can compute it. Though obviously we did not do it yet.
Yeah, something like that.
You can use large N or epsilon, like both case. Like if you, yeah, one can able to compute this number. It's possible.
So the effective action that you gave earlier does not. This does not apply for that fermionic, the free fermionic.
Free fermion case, yeah. If you just naively throw away the ground state Landau level, then it will be applied. But if you keep this, then in this effective action, that degrees of freedom also have to be included.
Those will contribute other non-local terms and that gain.
Exactly. If you try to integrate them out, that will give some non-local terms here.
Since you're keeping a background metric as well, you probably studying like strong gravitational field susceptibilities also.
Gravitational balance.
Yeah, possible, yeah.
But what was the reason to keep it there?
Just to take variations of the effective action and compute stress tensor correlators. No, for the sphere case, I am really putting this G mu nu 2 with a sphere background. So yeah, like here, so basically it's a non-flat G mu nu, but not treating the fluctuations, yeah, while evaluating this. Okay. So basically just I'm showing one example because rest of the examples even we could not write in paper, so we had to only write in Mathematica. So just the simplest one is basically the 2-point functions of the current correlator in momentum space. And if it is a Lorentz invariant theory, you will only expect just from the just the order identity gives the gauge invariance, will only allow this term. But since it breaks Lorentz symmetry, because like the time now there is no boost, so only you have the SO2 rotation in the spatial direction. There is another allowed tensor structure is also allowed. And also now the spectral densities or the form factor sometimes people call this. So the spectral densities are now basically not only functions of this k square, which is the 3 momentum square, but also it involves this k vector square, which is the 2 momentum square. Okay. And this is written just to make things dimensionless. And this is a dimension 1 object. So this tensor structure is dimension 1 and this spectral density is dimensionless. So, and these k vectors and etas are basically what they are explicitly written here. And one can use this effective field theory to compute the low energy expansion of this or the strong magnetic field expansions of the spectral densities in terms of various EFT coefficients. Similarly, one can do for the other things. So now once we have computed these things, we can ask the question is that can we be able to develop some dispersive argument and can we be able to put some non-perturbative bounds on the EFT coefficients? Yes.
The statement that at k equal to 0, momentum equal to 0, rho 1 is minus rho 2, is that something, sorry, rho 1 is minus rho 2 by 2, is that something one should have expected or something not really?
If I put k equal to really 0, so these terms vanishes exactly. So the tensor structures vanishes first. Then even if those are non-vanishing, it still vanishes, I think. Or this form factor relation.
Just the leading term, they seem to be half of the other.
I don't know whether this is a deep reason because actually gauge invariance tells that this and this two can be independent, this rho 1 and rho 2. So beyond that, yeah, maybe this is just a coincidence, I don't know.
Which terms contribute to rho 1 and rho 2?
Oh, this rho, for example, C0 is basically the cosmological constant term. Yes, the square.
28 terms in the.
No, not all of them are contributing. So they contributes, for example, JT or the TT correlators, but in the JJ correlators, only few of them contribute.
create one.
It's randomly arranged. Okay, it's just we gave the name like this is the 20 watts term. So I'm not just showing these are complicated expressions. So we have it in a list of expressions in our paper. Anyway. So yeah, there is we don't have any argument. So anyway, so now we can develop some dispersive argument and try to derive the bounds on these various CFT parameters. And usually in a Lorentz invariant theory, this kind of bounds or these dispersive arguments, to develop them, one usually use this Shalon-Raymond representation, where basically you write down the time order correlator in terms of some spectral density, and the spectral density expression is given here, and which is strictly positive when this k mu is in the forward light cone. And then basically tells us that at any values of k mu in the forward light cone, since the spectral density is positive, so its expansion in small k also has to be positive, and then basically this allows you to find bounds of different like combination of EFT coefficients to be positive. Okay. However, when we turn on the magnetic field, our effective field theory breaks the Lorentz symmetry. So obviously we cannot use this thing. There will be many problems, and the two kind of problems which arises is basically if we try to study, say, the time order correlator, for example, say in scalar operators or current operators, like current operators or stress tensor operators, it is not entirely clear to us what are in complex momentum space, what are their analyticity structures. And also, since the spectral densities are basically functions of now two like variables, which is the k square and k vector square. So working like how can we work in a like single complex plane, it was also not clear, and try to derive some kind of bounds. So for that, some progress actually earlier already has been developed by Senator and collaborators to study large charge CFT sectors, where also Lorentz symmetry is spontaneously broken. And we kind of generalized it, introduced stress tensors and other things to make it a more concrete setup. And so what we do, instead of starting with a time order correlator, we start with retarded and advanced correlators, where actually it is pretty clear how the analytic structures in the complex momentum plane are. And then we choose a particular configurations of this momentum k mu, so that only we need to work with a single complex variable, single complex parameter, and study the develop the dispersive argument in a single variable complex plane. And then basically, since the effective field theory gives us the time order correlator, so at the end we have to relate whatever bounds that retarded correlator gives to the time order correlators to find the bounds on the EFT coefficient. So these are the kind of logics which I will follow. So let's start with the definition of the retarded and advanced correlators. So let's consider there is a real operator. It don't have to be a scalar. So it could be like, as I will choose some combinations of tensors which are arbitrary. They don't have to be scalar. Consider some real operator O, and this is true even for the spinning operators. So, and then just what I'll assume is basically the translational invariance in the theory, because I know the Lorentz symmetry is broken.
But you have T invariance, right? So you only need to study one of them. Right?
T invariance means that T going to time reversal. Yeah, I have the time reversal invariance. That's true. So yeah, but so basically time reversal will tell me that how the retarded and advance are related. So basically, if I change x1 to x2, retarded goes to advance. But I'm just defining them because in the complex plane, like I will show that one, like in one side of the branch cut, this goes to the another retarded to advance. So just that's why I'm starting with both of them. So okay. So as so the retarded propagator is defined. So obviously in the x1 2, like it is basically like support. It has only support in the forward light cone, and the retarded propagator has the support in the backward light cone. And I will define the Fourier transform by just introducing a G tilde. And then basically, since obviously this is a function of k mu, there are 4 complex variables, and the spectral densities are 2 independent, like it's complicated. So it turns out that it is enough to choose a particular momentum configuration, which I want to obviously prove that, and that will give the extremal bound, that will give the extremal bound, or if you don't choose this configuration, that also gives the same bound. So what I will choose a particular momentum configuration to work with, so that I will have single complex variable. So the momentum configuration which I'll work is basically this k will be given by omega and 1 comma a vector xi vector. And this xi vector is a real 2 vector. Omega is basically the complex parameter. And this xi is basically bounded from 0 to 1. Okay, and if you choose this momentum configuration and then basically substitute it here and then use the fact that the retarded propagator is supported in the forward light cone and the advanced propagator in the backward light cone, from there you will able to argue that basically this gr of omega, which is basically with this momentum configurations, the retarded and advanced correlators, has only support in the upper half complex plane of omega, and the advanced propagator has only support in the lower half complex plane of omega.
This parameterization is so that if omega is real,
Mhm.
A is baseline, right?
Yes, exactly.
Not the correct.
Exactly. No, okay, sorry. Here, it's time like, sorry. Because the time component is always bigger than the modulus of space component. It's time like, yeah. So now since I start with the retarded propagator, so as I argued that it is analytic in the upper half plane. So then what could be the singularities there? So obviously, since we integrated out, since this is valid below some mass gap scale, and so starting from the mass gap of the theory, there should be a branch cut. And I'm calling this mass gap to be just omega cut. So there should be some branch cuts and other singularities, or there could be some stable particle as well, some poles. But whatever, I am ignoring this part. I'm just telling that there will be some singularities from there. And then since it is since this gr of omega is completely analytic in the upper half plane, so a contour integration over this object divided by omega to the power l plus 1 should give me 0. Only the fact that this l have to be positive integer, so that no other singularities appears from this power. And then what I want is basically that, so I want to basically then evaluate this object in different parts of the contour.
This is the condition you impose, or
which one? This one? So I'll first assume this, then I will choose a operator since as you. Oh, so first of all, as I showed that this is analytic in the upper half plane, so there is no other singularities in the upper half plane. So I just choose there is no other singularity, so this will be 0. So this is the choice of the thing. And then the thing is, the fact is that near omega equal to 0, the effective field theory is valid. So this, for example, evaluating this function on C0, I can use the effective field theory expansion. But the rest of the parts I don't know. So I have to use some properties of this Green's function there to put bounds on this near the omega equal to 0 region. But to do that, we have to also throw away the contribution from the arc at infinity. And since this can be done actually, because we will choose some operators of the theory, and we know that at very high energy, those are the correlation function of those are determined by the CFT. Because if I go a very high energy compared to the magnetic field, the scale of the magnetic field, then it will be denoted given by the CFT, and that basically fixes what are the high energy behaviors of them. So for a moment, I just assume that okay, the high energy behavior of this correlation function is given by omega to the power LUV. This is the power law behavior, and this LUV is basically what, depending on the operator choice, basically it's actually determined by the scaling dimensions of the operators in general.
So you're using the UVCFT to
evaluate the arc at infinity in a sense.
At least setting an L such that arc will be done.
Right. Yeah. So LUV is really fixed by the UV safety data. The
arc will be larger than LUV.
Yeah, but yeah. So to get rid of this arc at infinity, I can only work with this relation is only valid when L is greater than LUV. So they can throw the contribution from the arc. So then basically this reduces to evaluating this object on C0, and then the contribution from C1 and C2, and by proper change of variables, this can be written in this following form. And then finally, it will come the reality property. This operator I choose to be real, and that basically tells me that the retarded propagator with the say some complex value of omega will be same as the advanced propagator with this complex conjugate, and I can use this to relate to two different terms. And then once I relate it, if I choose L to be even, there will be relative sign. If it is odd, there will be a positive sign. And it turns out that if I choose to be L to be odd, L to be odd, then these two basically adds up, and there is you cannot have any positivity constraints from there. So that's why that's one of the reasons why we restricted to parity invariant theories, because parity odd theory will always give odd power in moment, and we cannot be able to use these dispersive arguments to bound them. So Okay, so then basically you use all these properties and then choose this L to be even, but above this LUV value. And then basically you can use these proper definitions of the retarded and advanced propagator, and this basically translates to this form. You after set like introducing complete set of variables and all this complete set of bases for the states. And then finally it reduces to the fact that now if you want to evaluate near this C0 contour, use the effective field theory, which has a polynomial expansion in small omega. And then basically what happens is that say the Lth derivative of this retarded correlator in the low energy will be given by basically the discontinuity, given by basically some positive function about this branch cut. So evaluate integrated over like from omega cut to infinity. And this object is positive because it involves mod square. So this basically tells us the retarded propagator, its L derivative for even L and L greater than LU, we have to be positive. But obviously, from the effective field theory, we computed the Green's functions which are time order. So we have to relate this, and it turns out that just from the definition, it follows that the retarded correlators will be given by a time order Green's function plus some contributions, and which have no support actually near omega equal to 0. So basically, this translates to the fact that this time order correlators times I, this coefficient of L derivative, are also have to be positive. But keep in mind that this is positive only for the momentum configuration choice when we choose this k mu to be this value, with the restriction is basically chi is less than 1. If it is greater than 1, actually all these analyticity arguments, whatever I describe, basically goes away. So then for our case, we just choose this operator to be a dimension 3 operator, which is basically del 0 of the current and the T mu nu. And this V mu, U mu nu are just arbitrary constants. You can think of this as some arbitrary tensors. They don't transform the Lorentz transformation. That's why I was telling this don't have to be a Lorentz scalar. And since it's a dimension 3 operator, so basically this LUV is basically 3, just fixed by the CFT correlation function. So basically then, since this VU and U mu nu is arbitrary, basically the argument here, basically this thing has to be true for all values choice of V mu, U mu nu. This basically restricts to the fact that this following matrix has to be positive semi-definite for the following choice of the K mu, and for the values of the L, like starting from 4, 6, 8, and all these orders. And our effective field theory gives the values for L equal to 4, 6, 8 of this object in the small omega expansion.
You're putting result for L even this.
Yes.
Because you've got this GR minus GA kind of.
Exactly.
Even for L odd, you will get something, right?
But that is not non-positive, not positive definite. So yes, exactly. From there, I couldn't be able to gain anything like or able to derive any bounds. So that's why I'm not considering those values of L's. And in our parity invariant theory, only even values comes in. So it's nice. So basically, then we had to use like our EFT, like we have like the EFT expansions to compute this object and solve for the semi-positive definite of this matrix for different components of like mu, nu, rho, alpha, beta choices, like choose 0, 1, 2 basically. So it's in general, it turns out to be 8x8 matrix for our case, because not all of the components J's are invariant because it's conserved and many other things. But finally, solving this thing, the kind of constraints which we got has this kind of following behavior, like this A, B, C, D's are basically some linear combination of Wilson coefficients, CNIs, and we got some constraints which are linear, constant, linear, quadratic, and cubic in this variable x, which is basically mod chi square, and they have to be solved for the values when in the range from 0 to 1. So basically, one can solve them analytically, those things, and one able to find various bounds as combinations of these or ratios of these ABCs for different numbers. For example, for up to 2 derivative order, with the expressions which I was showing, basically for the current, stress tensor current, and stress tensor correlators, one can found that this C0 have to be negative, C23, one of the Wilson coefficient have to be negative, and the combination of C21, C22, C23 have to be satisfied this condition with the condition this chi square runs from 0 to 1. And for example, it already tells that this C0 less than 0, if you remember, it appears the term which appears the leading term in the large magnetic field expansion to the susceptibility. So it basically tells that C0 less than equal to 0 implies that any 2 plus 1 dimensional parity invariant unitary CFT with E1 global symmetry will show diamagnetic behavior in strong magnetic field. And this is intuitively at least correct for actually, for example, free theories, because there we know the Landau level spectrum, right? And if we make the magnetic field strong, the free energy increases of the system. And with increase of magnetic field, if the free energy increases, that means this is really the diamagnetic behavior. But this is the argument which was that for any interacting CFT, this has to be true. And then also by solving these equations for this in the range xi square 0 to 1, we found also that in this, like the C22 over C23 and the C21 over C23, this also has a allowed parameters, like allowed region, and where only any unitary CFTs which goes to mass gap under strong magnetic field has to lie. And also we have plotted some C4Is, which I'm not showing here. Okay. So now once we have this bound, we can test whether some known examples we can put in the bounds, or if so I think
Yeah, could you go back once?
Sure.
These bounds and all don't depend on the value of B as suspected.
No.
Now suppose you took a non-uniform magnetic field. I mean, right now you're
For me, I'm putting in uniform magnetic field, yeah.
And just breaking Lorentz invariance down.
Yes.
And variance is still there.
Yes.
If you put slightly non-uniform, like slowly varying magnetic, can you, I mean, I guess derivative expansion will still work, right?
Yeah, so
You'll break it down further. Translation and variance also you'll do like this, but can you still do some level of analysis to put additional bounds?
So maybe those will be much more weaker than these bounds, for example. But also, if you break transformational invariance, like I have to possibly redevelop this picture what I was developing, these dispersive arguments I have to redo in this like more broken setup. So
at current level, it's like non-relativistic dispersion relation, like what dispersion relations we get in non-relativistic relation.
that's true actually. Lorentz symmetry is broken, so it's really SO2 invariance is only there, and all the translations. Yeah.
Can you do a further step of like taking some non-uniform background?
Yeah, maybe I did not think. Yeah.
One more level, yeah, scale of it. Also, probably many more Wilson coefficients.
Yeah, there will be many more Wilson coefficients also. Okay. So now I just want to, obviously, I would like to compute some interacting CFT like say Wilson, Fisher or Gauss-Neveu, but unfortunately, even for the free theories, the examples are too complicated. So I'll just show for the free theories only. So let's consider this free complex boson and turn on a background magnetic field. And this, if you turn on a background magnetic field, constant background magnetic field, which is basically this curly A when it is just A and A mu is 0. So then one can find out what is this like propagator for the complex scalar. Okay, and this has been computed. This is a remarkable result, like computed by like Swinger, where basically this is the paper where he developed this real-time formalism to study quantum field theory. And then so this expression is given here, and as you can see, the poles are exactly at the Landau levels. Right, so here I'm just written down in the Euclidean space. You can show the minus k0 square, basically this becomes. And these ln's are basically the logarithm polynomials. And then basically what you have to do, you have to basically start with this action and compute the 2-point function of the currents. And which basically taking variation with respect to mu and exponentialize this action, and which basically reduces to computing these objects, which involves these quadratics of these propagators. So I have to use these logarithm polynomial identities, play with it, then basically expand in small momentum. First do the loop integration, and then keep these sums outside, then do low momentum expansion, and then sums over these n values. And basically this gives some zeta functions, and kind of this expression basically roughly relates to this evaluating this kind of Feynman diagrams with the propagators, the complicated propagators here. And finally, one can able to read up. We only able to read up to 2 derivative order the FT coefficients, and independently, because at 4 derivative orders only using JMU correlator, we could not able to independently compute all of them because they comes with mixing, so we couldn't able to uncorrelate them. But okay, we computed, and these are the expressions. I will plot their values in the plot where they sits. We also studied for the free fermion case, which is basically we double the degrees of freedom, so 4-component Dirac fermion, so that we don't have this chiral anomaly problem. It's a parity-even theory. But still, the problem is there that there is a ground state which is n equal to 0. So this don't goes to gap. So this is not a good example to study. But suppose I naively run this sum from n equal to 1 to infinity, just forgetting about the like ground state. Then I can do this procedure and get a local correlators and then compare with the example. And then we can be able to read off these numbers. Okay. So just to show that now if I put these numbers in my plot, obviously the C0 conditions are both cases are valid, but at the two derivative level, the complex scalar lies well inside this region. However, this fermion, though it looks like in the boundary, actually it's little below, it's minus 0.337 off, which is kind of in the disallowed region, which basically tells that since there is a massless massless lowest Landau level which we ignored, and that usually gives some non-local contribution to the connected functional. So this basically tells that it has to be lie outside this allowed region. Okay. So this is because we just neglected the grounds.
It doesn't have to, but
it could, but it just it somehow is outside. Like for example, the zeroth coefficient C0, it satisfies the bound, but a two derivative boundary is just little below this boundary.
So from this, you know that there is no CFT where you can just throw
zero energy states. So so gapped, like all my construction based on the gapped assumption. So if there is some gapless mode remains, then basically it just tells that
Can I just throw away the gapless mode?
I can just throw away the gapless mode and do the evaluation. Okay, so I'm already I have still 2 minutes. That's one thing we can do. Like for example, say like this large NB or large NB, this Wilson Fisher or Gross-Neveu models one can do actually, and see where things. It's already very complicated because even this free fermion, the propagator as I was showing, it's too complicated to play with. There are these associated logarithm polynomials, and then their identities, and because they appears quadratically, then you have to expand. One is at momenta k, one is at k minus L. It's very difficult. Like even if it took like almost 3 months to work out these two examples. So I can put on a
computer.
We did in Mathematica in a sense, but still. Oh, okay. No, but the problem here is that we have to include all the Landau levels, right? N equal to 0 to infinity. It's really you have infinite number of poles. You have the zeta function regularization. So naively, if you count each terms, each of them sums looks like divergent. Only resumming all the terms, you will have the zeta function terms. So we need because all you see in terms of zeta functions.
But do you have wide logarithm ornaments sure? Because
Wide
at
logarithm.
some level it should be the symmetry of the hydrogen atom. Is there some intuition as to why the symmetry of the hydrogen atom is showing up here?
Okay. No, I don't have any. We just took the propagators from Swinger. Okay, he has he has in real time integral formula. We just Fourier transform, looked at they look nice. Now I can see the poles are really the Landau levels. Looks good. I can use Feynman diagrams, but okay. And then beyond that I don't have any interest. It's really very complicated. You have some integration over basically some proper time, like this. They introduce the proper time formalisms, and then it has also these logarithm polynomials there.
But the logarithm polynomial writing is in momentum space.
After doing Fourier. Okay, sorry.
But in momentum space, somehow you're getting a full
No. So there is no log. I don't now remember actually in how they looks, but the Swinger's paper has really the expression in Poisson space. You can look at very complicated. Okay. So now obviously as you are suggesting that we can compute for complicated theories, go and compute it. And the other interesting thing could be that now on top of this magnetic field, if we suppose turn on a chemical potential, what will happen? For example, we know that if there is a CFT with globally one symmetry, chemical potential turns it to a superfluid phase. Now suppose we introduce small magnetic field and increase it at which stage it basically make a phase transition from same superfluid phase to this gapped phase. So there could be some rich phase diagrams one can study possibly. And another thing is that, as I was showing, these S duality arguments kind of relates to the fact that like in one phase, like there is a superfluid phase and the other is related to really some gapped like Higgs phase by S duality. So now in the superfluid, like to study this, for example, this large charge sector of the CFTs, people develop this superfluid action. So can one able to see that through S duality, somehow it has some imprint, like we can come back to our effective action, like for the strong magnetic field, and there's some interrelation between them. And obviously, the another interesting example will be to study the holographic CFTs. For example, take this Maxwell-Einstein-Hilbert action and consider consider, for example, a magnetically charged black hole in the ADS bulk in the extremal limit, and then compute this current correlator and stress tensor correlators at the boundary. We tried to do it in our paper for this kind of a magnetically charged black hole in the extremal limit and evaluated this current correlators. Somehow, one of the bound which I was showing in terms of the C2s, this is also violated for this system, and we don't know why. It may be related to the fact that so one needs to introduce a temperature there, and one have to tune the temperature to be 0. And somehow, when you tune the temperature to be 0, it still has some entropy. So it looks like there could be still some massless degrees of freedom leaps to give this finite entropy or something, which I don't understand clearly. But at least in the one of the holographic example, these bounds are not like the numbers for the FT coefficient which we found are not in the allowed region, and we still don't understand why.
You didn't as a unitary
So there we just consider that a magnetically charged black hole.
No, in your various amounts.
Oh no, its unitarity is assumed because I think the positive condition. Yeah, here is basically where the unitarity is there.
So in that case, that a black hole that you have to violate the unitarity.
Yeah, it could be. I don't know. It could be that unitarity. Something has to be violated, either gap assumption or unitarity. Something needs to be violated. Otherwise, it should be in the allowed region. So, yeah, so more investigations are needed basically to understand what is happening. And with this, let me thank you.
Do you have any more questions? So what was the last 2 minutes of black hole? I lost it.
So one can study holographic CFTs, for example. So yes, for the black hole, and then to have a constant magnetic field in the CFT, you need really magnetically charged black hole in the ADS. Also, yeah. Also, so finally, since our case it's really t equal to 0 CFT. So if you start with the black hole, still you have to tune the t to be 0 at the end, right? So after computing this JJ at finite t, and you have to tune t to be 0. Because if you have to compare with our effective field theory prediction, yeah, you can compute it general for finite t, but to extract the CFT coefficient, you need to tune it to 0. That's the point.
Are you talking about the extremal black hole?
Yeah, near extremal black hole case.
Then the point is.
So,
The next statement.
so then you compute this current correlator on the boundary, putting in like near extremal magnetically charged background in the ADS bulk. And you can compute, suppose in principle you can compute it to arbitrary accuracy. Then you tune the temperature to be 0 in the boundary because it's given by a thermal CFT, so you have to tune the temperature to be 0. And then finally you have to do the small momentum expansion. And then compare with the EFT to read off these EFT coefficients.
So you're saying by a holographic calculation, you read all this C0s.
Yes.
And then see where they fit in that bond.
Yes. And what we found is that it's outside, it's in the disallowed region.
What was your 40?
It's just a Einstein-Hilbert, Maxwell-Einstein-Hilbert action in the ADS background with some boundary terms. And then we give this like field configuration, like this like gauge field configuration, which gives this kind of black hole solution. That's the bulk setup. And then from there, we want to compute the boundary 2-point function of the currents. So, okay, I am not an expert. So this one of my collaborator did this computation, and yeah.
The boundary value of the gauge field will determine the potential, right? Not the magnetic. What is the condition? to speak. So on CFT3, you want to fix magnetic field, right?
Yes, so and this magnetic field will come from the magnetically charged black hole in the ADS bulk.
That's why you have, otherwise you could have started with vacuum, right?
Yeah.
Get the magnetic field.
Yeah.
And that's why he's starting from a magnetically charged black hole.
Magnetically charged.
Right? If you think of the ADS as the sphere language,
Yeah.
right? The flux basically provides the boundary magnet.
Mhm.
That's the way it is.
And it's the flux that is keeping constant at the bottom.
But if you also put a potential, won't Maxwell gauge field,
Mhm.
won't it lead to some potential over the field and chemical potential?
The magnetic field.
The boundary value of NU is like a chemical, like
So
in
that
the
is electrical impact. I mean, you put electric
Elect-
potential.
Chemical potential, yeah.
but computation also is of NU correlator.
Yeah, the variation of the effective action with respect to mu in a sense. Like we can
In the bulk.
in the boundary. So
Boundary correlator is J mu J.
yeah, yeah.
So in the bulk, it should be read off as some extrapolate limit of NU.
Mm-hmm, mm-hmm. Okay.
This is not this area. This is not the coupled area. Yeah, this is the bulk.
You compute the bulk effective action. Yeah, I think what he is telling. Yeah, that's the thing.
Yeah.
The functional boundary.
Functional boundary.
Yeah.
They look at differentiation and then steady state.
Yeah, something a bit.
You take the other bonds.
Principle is possible, but it's computed.
Yeah. So you have a question?
You get the other bonds to be satisfied, like the susceptibility to be negative.
Yes, C0 is satisfied still there. Yeah. Somehow C0 is somehow insensitive of whether there is some gapless degrees of freedom. Or obviously for the black hole case, I don't understand actually why the reason is. But for example, this pre-fermion case, C0 bound is still satisfied there.
Maybe this is saying that your gravity is magnetic field, whose electric field is not a good bulk theory.
Yeah.
Could also be that he's first maybe some limit issue because he's working with this extremal black hole.
Yeah, that's also actually that.
The order of limits may be.
Yeah, because at the end we are only taking T going to like the temperature going to zero limit, and maybe order of limit could be important also. Yeah, that's also a problem.
Finite temperature from here.
So yeah, that's actually one of the interesting thing that we can okay, people studied this finite temperature EFT for conformal field theories, right? Like starting from Siraj Minola and then also recent papers by David Simmons, Raffins and collaborators. So what they do is that they also introduce, like to study this, they use this background metric G mu nu and then compactify the time direction to construct these effective field theories. So I don't know how to connect to this system and then suppose I introduce a gauge field and give a background gauge field and study both the systems together. The problem will be that now there are two scales. One is temperature and one is magnetic field. And in general, this kind of systems, it may turn out that there could be two while invariant matrices and then one's metric. Like I have only G hat is the one. For example, maybe, yeah. So then I don't know how to write effective field theory. And this happens even in 4 dimensions. Just take 4-dimensional CFT and just turn on background magnetic field. Okay. Like here I was showing there is a single G hat metric. So because of this Cayley-Hamilton theorem that basically if you have antisymmetric F mu nu, only at 3 dimensions, only F square is the only scalar. F to the power 4 is determined by F square and F cube is 0. So if you go 4 dimensions, then F square and F to the power 4 basically are both independent, and you can use both to construct 2 independent wall invariant matrix. Then I don't know how to write effective field theory which has 2 independent background matrix. So I don't know how to run my process there. So that's a big problem. That's why we had to restrict to 3 dimensions. One of the reason also.
You start times until now, can you not increase the volume of S2 to infinity?
So the volume of the S2 is the L square part. L square basically.
Times.
R2
But maybe the magnetic field will be very.
So the magnetic charge will also go to infinity in that limit. So let me
Unless you take some.
go back there. So here you are telling that I want to scale L to be infinity basically.
start with that, and you computed the effective, the free energy, right? And
Yeah, yeah.
Multiplied the R.
Mm-hmm.
Now you take L to infinity,
Right.
keeping Q fixed perhaps.
Actually the free energy vanishes because I multiplied by a factor of L here. You see, just
Yeah, I mean you need to look at density.
yeah. I need to look at the density. Yeah.
I don't know that will help.
Yeah, I think what may happen is basically if you, I think that, okay, maybe the effective. So what happens is that if I put this R2 cross S1, actually I think this Ricci scalar and all these things will vanish. For example, this S21, S22, all this won't contribute, right? This effective actions. Right, but if you take sphere to be in, yes, it has some magnetic field contribution. I should have written down.
Here's the calculation that you've already
Mm-hmm.
But can we interpret this as some kind of thermal answer in the magnetic field if you take an appropriate? I don't know if it's.
That beta is like same as the black will be the same as black hole beta.
No, just thermal CFT is telling. Like forget about that ADS picture, say for a moment. Just thermal, and then okay, I understand. If I take the sphere scale to be infinity, then it's really thermal circle is there only present, and whether
Care about because in S direction is flat. S1 beta is already flat. Is it not?
Sure. Yeah.
no, but he is saying that it is r hat mu nu has the information about the field state. One is expanded, it will have r mu nu plus say nabla nu over f or something.
This answer be the answer for if the magnetic field at the finite nature is at least some contributions.
Yeah, I understand your question. Yeah, I understand your suggestion actually. Yeah, I understand. Yeah, I can check it seriously thinking, but this is a good suggestion. Yeah, just take this answer and do this limit. Yeah.
It's too many papers in 1951.
Oh, okay.
Which paper of
Uh-huh.
Spiegel? Which paper of Spiegel?
This is 1951 paper where he derived this propagate. I think the name of the paper is possibly that fermions in magnetic field or Dirac fermions in magnetic field or something like that.
In that phase production paper, he does both electric and magnetic.
So yeah. So in that paper, I think he started with just a mu, which is this A, which is just constant like A, and he did not assume anything, right? And then at the end, so he has a formula, but at the end, when you try to find a kind of expression which is closely like close to, at least in the momentum space, if you don't consider this to be restrict to constant background field, you won't be able to get something nice, as I was telling. But I feel that, like, okay, he started with very basic, maybe I think introduction in one section, then he took this background that its magnetic field is there. Because his paper only does this. But then people try to obviously generalize this when there is both electromagnetic field, constant electromagnetic field, and try to do it. But I did not follow much here. I can send you the paper. I have it. Don't worry. Mm-hmm.
I mean, it is not true that if you take any, I mean, effective field theory in ADS, it will generate a good CFT. It will generate a good CFT only in the sense that it will satisfy all the standard body of the general body. Yes. But
the stress strength
relation, etc., are very complicated properties of.
But even so, what identity, the stress tensor what identity may not be satisfied, right? Or
I think if I start a general coordinate invariant theory in the bulk,
there will be okay.
yeah, the stress tensor what will be satisfied,
Okay.
but not the dispersion relations and so on. Right? That really requires a good quantum theory in the bulk.
Yes, it has to be. It has to give some unitary CFT. That's
Exactly.
the assumption.
You need a proper good quantum theory in the bulk.
Have this property.
If it is so cheap, then you take any arbitrary effective feature in the bulk and you have a CFT.
Which is a good CFT. All assumptions of the CFTs are satisfied. That's true. That's true.
In any dimension is hard.
Mm-hmm.
So I have a feeling that if you take a generic bulk theory, right, if it comes from some particular string background, right, then one can say, okay, now it should be a good CFT.
Mm-hmm.
But otherwise, I don't see why it should be satisfied.
Even general supergravity, you would say, may have this problem, right?
Yeah, supergravity, you have to, I mean, maybe the point is that you can find that the stringy collections can be ignored.
Yeah.
And
From the
then
bulk.
supergravity, yeah, from the bulk, but then supergravity. But it has to be something that you know is a good one. right? Which can get into a good quantum field in the quantum.
Like by adding string iteration, quantum string iteration.
Exactly. Because otherwise you can very easily construct CFTs, right?
I understand. Yeah. Yeah. All gravitational background are good quantum gravity background. I don't know. Yeah, that's true. That's true. This should not be the truth. Yeah. Yeah, maybe we see this artifact in the bounds that it's not satisfying the bound. Maybe could be the reason.
In fact, if it's a good quantum,
Good quantum theory. Yeah.
part of the swamp land.
Yeah.
Swamp land paper.
For APJ, can we just
Yeah, on APJ, we
what such thing can it not be fit into that APJ plane?
Yeah, maybe one should be able to fit into ABJ because that there you know it's a good quantum theory, right? And one can ask if
But maybe you cannot ignore some of those.
yeah, ABJ has certain number of fields, right? I mean here, what I understood is you
Get to
just did the minimal one gauge field and one spec. So and with that we found this issue.
Right. So,
you start with ABJ kind of.
but here this is just the non-dynamical one, right?
But it have couplings to the other fields. So
Okay.
effective action, I think there might be other quantities.
Okay.
can you truncate ABM to just Einstein? Some configuration of Einstein.
No, but the fluctuating fields will have all that.
There is this semi-classical way of doing some GK prediction. Just JV correlation function. I want to read off from on-shell action in the bulk.
So that you can do.
Yeah, but it may not still be a good.
Yeah,
What
because
is
that's
that?
really right. This concept will also it may not be one field that is a global one, but it may be multiple. You cannot just declare that I have one from some particular field carry a global one, that and that.
If it solves the equation of motion by
So that still may not be a good quantum theory.
you already said ABGM is a good quantum.
Yeah.
And I take ABGM and I look at the equation of and I provide a configuration to you. Black hole with a magnetic field.
But I think for there you have to take it.
It may not be a consistent configuration.
Yeah, exactly.
Other fields also will get charged automatically.
Exactly. That's what I said. Yeah.
Okay.
Because other fields will automatically get charged.
What is the content of it?
That is a complicated.
That's complicated.
Yeah.
What is the string?
How do we get it from
Like what is the type to be
Yeah,
like what is that?
Very story.
What's the theory?
I think yeah, consistent transaction has got that. But it has a lot of fields.
Yeah. In particular, it has some more fields than ours, not just the.
Exactly. Yeah.
That's right.
Okay, if there are no more questions, let's thank.
Did you find out the paper? Or
I saw it in your paper.
Okay, we cited there. Okay.
You're basically looking at this K mu nu, right? The K mu nu is their propagator.
Yes.
You're basically saying that this K mu nu, once you do the sugar parameter integration, becomes Laguerre.
Yeah, exactly. So some later papers actually did it. So maybe this paper also has done it. If you scroll down, it has, I think. But we took it from some recent review where at least factors, if there are some errors, they fix the factors.
Okay, thank you.
Thank you.
Yeah. Exactly. You get part of that.
That's like construction between streams. Suppose I want, let's say, a geometry like ADS7 plus S4.
That is
Then I know. Or like I need ADS 9.
It's not there.
ADS 8 cross.
It's not there.
No, it's not there. People not found.
People haven't found one.
Yeah. So I'm saying if I produce it this way to try and embed this diagram within a known string theory.
Yeah, but I'm very
And find the object flux from that consistently solve the equation. But if I can do this, that will give automatically assign a CFT on the boundary. I may not be able to identify the field content
that easily. But if you have an ADS find any ADSD that's A solution, right?
Of string theory, for one of the string theory. Then string theory is a good fund for gravity. Everything is well-defined. That nothing there.
Yeah.
And it will get automatically satisfied. The boundary theory will automatically satisfy the axiom
Yeah.
on some
Right.
CFT. CFT. Yeah.
But is there any of this kind of solution? No, like we don't like this ADS for